Hello, good evening. So I hope I am audible, and welcome you all to the seventh and eighth week of Great Live Mentoring session of Phase 2. So as I informed earlier, today will be a 2 hours of session. So today I will cover few concepts regarding the uh, this concept will cover. First will be the solution model. Different solution model we will cover here, like ideal solution model and regular solution model. Okay, then we'll talk about the free energy versus composition diagram, and then we'll move to the concept of miscibility gap. So also we'll also solve few questions. Mostly these questions are will be related to this solution. uh, so that's why I'll first cover those topic first, so that it will be easy to understand. So most of the questions are related to the solution. uh, so that's why I it will be better if I cover the concept of the solution and free energy versus composition diagram. Then I will move to the different questions, and then we'll solve the question together. Okay, so let's start. Before starting the before discussing about the solutions, so first we'll discuss few concepts regarding of the thermodynamics. So how many of you know about the chemical potential? uh, can you tell me what is the chemical potential, how we'll define it? Anyone? So this you know, right? G is equal to H minus Ts. This is the one equation that is important for today's session. Another concept is chemical potential is so what is chemical potential? Chemical potential, the change in Gibbs energy with addition of atoms. Okay, you can uh, you can explain it in more elaborately, like uh, few informations are missing from your definition. So the thing is that let's say this is your some system. Okay, so the free energy is let's say now is G. Okay, and it is, let's say, mixture of A, B, and C, or many atoms, let's say. Okay, now we have you are adding few moles of or dn moles of A atom. Okay, so then chemical potential is defined as change in free energy per mole of addition of any element in at constant temperature and pressure. So that is also important. You should mention at constant temperature and pressure, and when the composition of the other elements are fixed. So like so mathematically you can write it as chemical potential of A is equal to change of free energy of the system. Okay, not change in free energy of element A. Okay, so change of free energy of the system per unit mole of addition of element A. So dg by dna when temperature, pressure, and nb, nc, and up to ni. So this thing will be constant when your temperature, pressure, and number of moles of the other element are constant. You are just adding only a n mole of dn mole of a. So then what your change in free energy, this is known as chemical potential. Okay, so chemical potential is also, you can write it as partial molar free energy. Okay, so you can also write it as G bar A, which is equal to, which is known as also partial molar free energy. So similarly, how we can write mu B? Mu B also similar. It will be dg of the system, change of free energy of the system, divided by dnb per unit mole of addition of your B. Okay, and when temperature, pressure, number of moles of A, number of moles of C, and dot 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 up to number of moles of I. All the other number of moles of the other elements are constant. So this way we define the chemical potential. So chemical potential, I hope every one of you know what is chemical potential. Okay. So this concept is also required when we will go for the go for we'll write the expression for the free energy for the solution. So in previous class we have talked about how free energy changes with temperature, right? So G versus T plot we have seen in our previous lecture. So there we saw that your G and T, so the free energy varies like this, right? With temperature, free energy decreases because G is H minus Ts and your slope is minus S, and with temperature S increases, so your S is positive, as and as S is positive your slope is minus S, so minus S means slope is negative. So free energy changes with free energy decreases with temperature. Okay, so now if we add one more variable, like if we this is if for pure element, G is a function of temperature and pressure only, right? But let's say if we add some other element to it, like you have few xa mole of A and xb mole of B. So now you are adding this also together. So then there is one more variable comes into the picture, and that is your compositions. So for pure element, your G is a function of only temperature and pressure. But for alloy, G is a function of temperature, pressure, and number of moles of, of element I, let's say. Okay. So in this case, one more variable is there. So now we can also see how the free energy will vary with compositions at a fixed temperature and pressure. So we can also draw a graph which will where G is in the x-axis and your xb is in the sorry G in the y-axis and xb in the x-axis. So in this case, how the free energy will vary with composition, this thing we will see today. Okay, so now we'll draw the graph later. First let us discuss what will be the expression for the free energy when, let's say, initially we have a mole of xa mole of A atom and xb mole of B. Okay, so when those are separated, not mixed together, then the free energy or molar free energy of element A is Ga, and molar free energy of element B is Gb. Now if you mix Xa amount of A and Xb amount of B, then what will be the total free energy? So initially your Xa mole of A was there, and then and xb mole of B was there. Okay, xa and xb. Now we are mixing it together. A and B is there. Okay, so total is xa plus xb, that is equal to 1. Okay, so now if the free energy, molar free energy, is Ga, and for this if the molar free energy is Gb, so what will be the free energy of this your, let's say first consider physical mixture, no solution or no interaction is occurring. So if it is just a simply physical mixture, what will be the free energy, total free energy of this system? Anyone? Let's say if it is only physical mixture, what GA plus GB. Yes, go right. So this will be GA plus GB. This is only if it is just a physical mixture. So that means no interaction is happening at all with your with between the atoms, between the A atoms and B atom. Okay, but in reality this is not the this is not the scenario. So in reality what happens when you are adding A and B atoms together? So rather than being a physical mixture, it also like interact with each other, and also so this is only for physical mixture. But when solution of A and B is taking place, that time you there is a free energy change is there. So that free energy change is termed as delta G mix because of the solution. So what will be the free energy of your solution? Solution will be G of your mixture. Mixture means physical mixture I am talking about here, plus delta G mix, or delta G solution also you can take. So delta G mixing. So this two term is there. If only physical mixture, then only this term. But when solution A and B are dissolving in each other, there delta G mix term is also you have to add. And because of these things, so delta G mix we can write it as, let's say we'll talk this thing later. So let's hmm. So delta G mix we can write it as, okay. So when A and B atoms are mixing with together, so there will be two different situation will happen. Like one is interaction between the A and B atoms. So if your solution is non-ideal, then A and B atoms will interact with each other. Okay, and another, so that interaction thing is taken care of by the delta H mixing term. Okay, and let's say if your solution is ideal. So for ideal solution, what is the value of delta H mix? Anybody of you know what is the value of delta H mix for ideal solution? Yes, you are right. It is 0. So for ideal solution, delta H mix is 0. But even delta H mix is 0, like delta H mix 0 means it is basically stating that there is no interaction, right? So delta H mix 0 means there is no interaction between A and B. But still, your free energy decreases because of the configurational entropy. Okay, so this delta S mix is because of the configurational entropy. Like when you have pure A, only A atoms are there, there is no certain kind of arrangement is possible, right? Like everything will be almost similar, like all the atoms are same, all the atoms are A. But as soon as you are mixing some B atom with your A atom, then there is a probability is there for the different configuration. So because of that configuration, the configurational entropy arises. So I think all of you know what is the configurational entropy. Delta S config is written as K into ln of omega, right? Everyone are aware of it, like you know, right? Delta, what is K here? What is K? Boltzmann constant. Yes. And the omega is the different way in how many way you can configure, you can arrange your atom. So the number of way you can arrange your atom. So this is your omega. Okay. So if you derive this thing like omega, like for n, capital N number of A atoms, or let's say small n of A atoms and small b of n of nb atoms are there. So omega is na factorial plus nb factorial by na plus nb factorial, right? So then if you just derive it, you will get that delta S config as minus R xa ln xa plus xb ln xb. So I think all of you know this equation, right? What is the delta S? So this is the equation for delta S, and so then how we can write delta G then, G of solution then. So G of solution is G of physical mixture plus delta G of mixing, right? So we can write G solution is equal to XA GA plus XB GB plus delta G mixing. So this will be delta H of mixing minus T into delta S of mixing. So delta S configurational is basically your delta S mixing. So delta S mixing is, so it will be minus minus, it will be plus RT XA ln XA plus XB ln XB. So this is your equations. This is the your equation for the G of solution. Okay. So now there is, as I also told earlier, for ideal solution. So let's say case one is for ideal solution. Okay, let me go into the next page. So let's say case one. So this is for ideal solution model, your delta H mix will be 0, right? So if the delta H mix is 0, then what will be the your G of solution? G of solution will be simply XA GA plus XB GB plus RT XA ln XA plus XB ln XB, right? So now we know that G is a function of temperature, pressure, and number of moles of A. For binary system I am talking about now. So for binary system, it is sorry, Na and Nb both will be there, right? So if we take integral enthalpy, sorry, it will be integral free energy. So as we are taking Na and Nb, we are not taking Xa and Xb. Okay. So now if we write in terms of partial differential form, so it will be del G by del T at constant pressure Na and Nb into dt plus del G by del P into dP at constant temperature Na and Nb plus del G by del Na at constant temperature, pressure and Nb plus del G by del Nb, sorry, there will be dNA dNA, okay, temperature, pressure and Nb plus del G by del Nb dNb, constant temperature, pressure and Na, right? So now let us assume this solution is happening at constant temperature and pressure. So at constant temperature and pressure, what will be the, at constant temperature and pressure, this dt will be 0 and this dp will also be 0, right? So that means only this term and this term you have. So now, as I have also discussed earlier, What is the dg by dna at constant temperature, pressure, and nb? What is this thing? What is this? Anyone? At the beginning of the class I have yes, chemical potential of a and chemical potential of b. So this is the chemical potential of a and this is the chemical potential of b. Everyone understood this up to this part? So you can write del g prime is as mu a dna plus mu b dnb, right? Okay, so now if we integrate this thing, we'll get up to 0 to na plus nb, because this is the free energy of your total system. So total system is your na plus nb, right? Integration of mu a dna, this will be 0 to na, because this is only for a, and similarly 0 to nb mu b dnb. So sorry, so now we can write as ga, sorry, g prime is equal to mu a na plus mu b nb. So this is integral free energy, right? Now if you divide g prime by na plus nb, you will get molar free energy, right? And mu a into xa plus mu b xb. So this we got dividing by na plus nb. If you divide both of the side by na and nb, you will get like, if you sorry, uh, g by na plus nb is your this is integral free energy. If you divide it by na plus nb, so this will be your molar free energy, right? So similarly in this side, if you divide na divide by na plus nb, it will be xa, right? Similarly if you divide nb by na plus nb, it will be xb. So we can write that g in terms of chemical potential. So this is the g of solution in terms of chemical potential, and this is g of solution in terms of mole fraction and free energy of your pure uh, free energy of pure A and pure B, molar free energy of pure A and pure B. So let us consider this is as equation 1, and let us consider this as equation 2. So from the equation 1 and equation 2, if we compare, what we will get? So I am writing in the next page the equation 1 and equation 2. So equation 1 was G of solution is equal to xa Ga plus xb Gb plus RT xa ln xa plus xb ln xb. So you can rearrange it a little bit. In and equation 2 was G of solution is mu a xa plus mu b xb. Can you rearrange this equation 1 and then compare with the equation 2, and then find out what is the mu a and what is the mu b? You can unmute and answer also, no issue. So yes, mu a is equal to Ga plus RT ln xa. Okay, okay, good. Everyone getting the same? So just take just rearrange your equation. Take this part of this and this part of this, and take xa common. if you take xa common, it will be Ga plus, from this if you take xa common, it will be RT ln xa. Similarly, from this part you take xb common and then write Gb plus RT ln xb. Okay, so now if you compare, this is xa and xa is there, so your mu a will be this one and your mu b will be this one. So this is mu a and this is mu b. So we can write as mu a is Ga plus RT ln xa, as mu b is Gb plus RT ln xb. And as I told earlier also, like mu a is also known as partial molar free energy of A, and this mu b is also known as partial molar free energy of B. So partial term is denoted as G bar, Ga bar or Gb bar. So this is the two important equation. So these two equation and also this one, this equation also important. Okay. So now so far we have talked about ideal solution, right? So what will be the situation if the solution is not ideal? Let's say for ideal solution, there was no interaction between element A and element B. But what will be the scenario if the element A and element B, there is interaction between these elements? Then in that case, your delta H mixing will not be zero, right? So if there is a let's say case 2, regular solution. So now we'll discuss the regular solution model. So in case of regular solution model, your delta H mix not equal to 0. Okay. If delta H mix is not equal to 0, then your whole equation will be this thing, this one. Yes. So if delta H mix is is not equal to 0, then you also have to consider delta H mix value in your equations. Okay. So now there is if you will consider regular solution model, there is a one approach is there which is called quasi-chemical approach. So using this approach, we will find out what will be the delta H mix value. Okay. So now let us move how to calculate the delta H mix for regular considering the regular solution model. Okay. So okay, I think sorry. Okay. So this is based on the quasi-chemical approach. Okay. So in quasi-chemical approach, it is assumed that your the enthalpy is totally dependent on the your bond energy. So this is the bond energy, bond between A and A atoms. This is bond between A and B atoms. So it is assumed that, so this model assumed enthalpy change bond energy. So there are different bond energy. One is for A and A atom, which is, let we write it as epsilon AA. Bond energy between epsilon A and B atom. So this is we write it as epsilon B and B, and bond energy between A and B. So this is epsilon A and B. So as assume in this model, as your bond energy is totally dependent on the your enthalpy is totally dependent on the bond energy of your different energy of your different bond. So we can write as H of your solution. So H of your mixing basically or solution. This is the probability of finding, P is probability of finding A and A bond into epsilon A and A. Okay, plus probability of finding B and B bond into epsilon B, and probability of finding A and B bond into epsilon AB. So up to this part, you people understand. So if you mix A and B atom, so there will be three types of bond will be possible, right? One is between A and A atom, another is between A and B atom, and another one is between B and B atom. So we have total three types of bond will be there, and probability of finding this kind of bond in multiplied by the bond energy. If you take the summation of this will be the total enthalpy of your solution. Okay. So up to this part, everyone understood? Okay, okay, okay. Give me a second. I'll be back. Hello. Yeah. Uh, okay. So this is your. Now we have to find out what is the probability of finding a bond of A and A atoms, probability of finding bond between B and B atoms, and probability of finding bond between A and B atoms. So let's say this total system, it is 1 mole. Total number of moles of your system, it is 1 mole. Total system is 1 mole, where you have XA mole of A atoms and XB mole of B atoms. Okay, and the coordination number is Z. So everyone of you know, right, what is coordination number? What is coordination number? Yes, number of the nearest neighbor of that particular atom. Okay, so now for the time being, just consider any one atom. Let's say we are considering this A atom. Okay, if we consider this A atom, so it is how many neighbor it will have? It will have Z number of neighbor, right? If the coordination number of this system is Z, it will have Z number of neighbor. Okay, so what will be the probability of finding A and A bond? So it has Z number of neighbor, but all the Z number of neighbors will not be A atom, right? Because you have B atom also in your system. So how many mole of B atom is there? XB mole of B atom is there, and XA mole of A atom is there. So probability of finding atoms is Z number of atom we will find, but probability of finding A atom is XA. So sorry, probability of finding A atom is XA. So your probability of finding A type of bond will be Z into XA, right? XA, but your total system is N mole. Sorry, 1 mole. So in 1 mole, how many number of atoms are there? Total, how many number of total atoms are there? Yes. So you have Avogadro's number of total number of atoms, right? So Na, let's say Avogadro's number, we write it as Na. So total number of atoms is Na, and in your total in your total number of atoms, your X fraction is your A atom. So this is the your total number of A atom, right? This is total number of A atom in your system. So this A atom is surrounding by Z number of atom. So this atom is surrounding by Z number of atom. But all the Z number of atom will not be your A atom. So the probability will be your coordination number into XA into Na. Okay. So this is the sorry. So one Z and X will be your probability of finding A atom. So one more XA term will be there, like ZXA. So this is so Z into XA is your probability of finding A atom nearest to this A atom. But this is not the only one A atom you have in your system. So you have total how many number of A atom? You have total XA into N number of A atom in your system, right? So if you consider only this one, then it will be only this part. But if you consider all the A atom, like this A atom and what is the surrounding atoms is there, if you consider all the A atom and do it like this, so you will be so you have to multiply it by total number of A atoms. So XA into Na is total number of A atoms, right? But when you are talking about bond between A and A atom, you are considering two A atom together, right? But for two A atom, how many numbers bond is there? Only one bond, but two atom, right? But here we are talking about probability of finding bond, number of bond between A and A atom. So this will not be only total number of A atoms. You have to find out total number of bonds between A and A. So we have to multiply it by half. So basically this is the total number of A bond, and this is the probability of finding A atoms nearest to any other A atom. So if you write this, then it will be PAA is equal to half into NaZ XA square. So everyone understood up to this part? This is very important. So try to visualize this thing. Uh, if you have any doubt, you can ask me. I will explain again. Everyone understood? Okay. So I hope no one has any doubt up to this part. Okay. So similarly, can anyone tell me what will be the PBB? What will be the P half into Na Z? In this case, it will be XB square, right? Understood? Now, tell me what will be the PAB? What will the PAB? Anyone? Try to visualize. If you have understood that up to this part, I think you people can answer it. So consider one B atom. So it will surround by total Z number of atoms, as the coordination number is Z, right? So let's say this one is on the top side and one is on the bottom. Let's say in this case, let's say you can assume 6 or something, or Z also you can find. So coordination number is Z. So one B atom that will be surrounded by total Z number of atom. So total Z number of atom it will be surrounded. Now what will be the probability of finding any A atom nearest to this B atom? What will be the probability? Similar to this only. If you see this, if you see this, Z number of atom is surround total number of atom is Z. Now what is the probability of finding A atom nearest to this A atom is Xa, right? Because the probability is their mole fraction only. You see this is your B atom, so it is surrounded by many number of total Z number of atoms. So the probability of finding A atom nearest to this will be Xa, because you have Xa mole fraction of your A atom. So this is will be multiplied by Xa. When you are saying about probability of finding A atom nearest to any B atom, it will be multiplied by Xa. But if you consider any A atom, and then it will be surrounded by total Z number of atom, right? Now if you are talking about probability of finding any B atom nearest to this atom, what will be the probability of finding any B atom nearest to this A atom? This will be mole fraction of B atom. So when you are talking about probability of finding any which atoms, that atom's mole fraction you have to multiply it. Okay. So similarly, this is the your probability of finding AB type of bond. Okay. Now total how many number of AB type of bond will be there? So this is the probability of finding any B atoms nearest to it, right? But total number of your how what is the total number of your B atom is there? This is here you are considering only one B atom, right? So one B atom you are considering, but in your system total number of B atom is Na into Xb. So this is your total number of B atom, and this is your probability of finding A atom nearest to the B atom. So in this case, you are considering one A atom and considering one B atom. So that's why Xa and Xb is there. But in this case, you are not considering two A atom or two B atom. In earlier case, for AA type of bond, you are considering two A atom. So that's why you have multiplied it by half. In case of BB type of bond also, you were considering two B atom. So here also we have multiplied it by half. But in case of AB atom, one is A atom and one is B atom. So you are not counting the same atom twice, right? So in this case, we no need to multiply it by half. So in this case, your PAB will be NaZ into XaXb. So up to this part, everyone understood. So no one has any doubt, right? If you have any doubt, you can ask me at this point only. Otherwise, later you will find difficulties. If everyone is okay with it, then I will move. Okay. Okay. So now we have find out what is the total number of BB type of bond, total number of AB type of bond, and what is the number of AA type of bonds. Okay. So initially, when you had pure A, let's say there only pure A is there, and pure B was there. Okay. Now when you are mixing, there you have A and B, both kind of atoms are there, right? So now in this case, your what was your enthalpy? H of A, P of A into epsilon of A, right? According to the quasi-chemical model, what it assumed that enthalpy is totally dependent on the bond energy, is solely dependent on the bond energy. So if your bond energy is epsilon A and PA, okay. So in this case, all the bonds are AA type. So in this case, your PAA is 1, right? But in this case, your in this case also, H of B, what is this? This is PBB into epsilon BB, right? But in this case also, it is pure B. So this is pure A and this is pure B. So in pure B, all the bonds are BB type, right? There is no AB type of bonds or there is no AA type of bonds. So in this case also, your H is equal to epsilon BP. But when solution is taking place, that time you have three types of bond: AA type, BB type, and AB type. So the three types of bonds are there, and probabilities we have already found out. So in this case, your H of solution is equal to P of AA epsilon AA plus P of BB epsilon BB plus P of AB epsilon AB. So then, what is the enthalpy change when solution is taking place? What is the enthalpy change? So enthalpy change is delta H of mixing. We can write it as H of solution minus H of A plus H of B, right? So now H of solution is P of A. So we'll write this thing here. So P of AA was half NA Z XA square into epsilon AA plus half P of BB was half NA Z XB square plus P of PBB was NA Z XA XB into epsilon AB. So this is the H of solution, and we have to minus that this part. So this part is epsilon AA minus epsilon BB. Here also we have to count the total number of bond, right? Here in case of PAA, we have to count the total number of bond. Subramanian, what is your question? Considering enthalpy of A, we have XA mole of A. Yes, yes, yes. So yes. So there is one mistake. So in this case, total number of moles is 1 here, right? And we are adding XA mole of A and XB mole of B. So in this case, PAA and PBB is not will be 1, because total number of atom we have to consider. So you are right. Yes. So in this case, your H of A will be, so total number of atom is NaXA by 2 will be there because we are considering the bond, and then epsilon AA. Now it is right, right? I guess now it is right. And similarly for H of B, it will be if we take this thing common, it will be Na Z X X B. It will be Z into epsilon AB minus plus this part will be the Z into XA by XB. The final expression should come Na XA XB to Z in epsilon AB minus half of epsilon AA plus epsilon BB. So this term will be independent of XA or XB. Anyone is getting after simplifying this equation? Anyone of you are getting? I think we have to multiply XA plus XB there. There was a trick like this is 1, so we can multiply it here. And here also XA plus XB we can multiply. Yes. So now if we multiply this XA and XB, so it will be yes. Now we can get. So this is half of Z, and here also Z has to be there because your one atom is surrounded by Z atom, right? So here also you have to consider the coordination number because one atom is surrounded by Z atom. So there is a probability of finding Z number of bonds with this single A atom, right? So here it will be Z is there, Z is there. Now as XA plus XB is 1, so we have to we can multiply uh, 1 with this. So that means XA into XB we will multiply. So if we multiply, we will get half of Na Z XA square into epsilon AA, and from this we'll get minus of half of Z Na XA into XA will be XA square, right? So this two part will get cancelled out, and the other part will be there. Other part is half of N Z into XA XB into epsilon AA. Epsilon AA will be there. Epsilon A will be there. So similarly for this also, XB square term, this term and minus is there. So when you will multiply XB with XB, so it will become XB square. So this term will also get cancelled out. So only this term will be there. Only minus of half N A Z Na into Z into XA XB epsilon BB, this term will be there. So and this term will be also there because it will not get cancelled out from this term. Okay, so it will be plus of Na Z XA XB epsilon AB. Now if you have if you write it in the simplified form, it will be, if you take common Na Z XA XB, then epsilon AB term will be there, then minus of this half will be there, sorry, this half will be there, and then plus epsilon AA. Yes, so this will be the final expression. So I think now everyone of you understood this part. So what we did here, everyone understood, right? Yes. So here also basically you have to consider Z and Na into Xa both, because one A atom is surrounded by Z number of atoms, right? So if we just consider only one, then it is wrong. So you have to consider Z number of atom because coordination number is Z, and total number of A atoms is Na into Xa. So this will be the final expression for your uh, delta H mix according to the quasi chemical approach. Okay, so this we can write it as omega into xa and xb. Okay, so delta H mix we can write is as omega into x into xb, where omega is equal to na into z into epsilon ab minus half into epsilon aa plus epsilon bb, right? So what will be the final equation for your g solution for regular solution? It will be xa ga plus xp gb plus delta H mix will be omega into xa xb. So this term I am writing as omega. Okay, this is called interaction parameter. So omega is interaction parameter, and plus that entropy term will be there, that is RT xa ln xa plus xp ln xp. So now what was the equation for ideal? Okay, let me just rearrange in first entropy term, like in terms of ideal solution, and then in terms of then it will be easy to understand. xa ln xa plus xp ln xp, and then that in delta H xa and xp. So in case of your ideal solution, only up to this part was there, right? This part was for the ideal, and this part is your excess than ideal. So this is for regular solution model, the G of solution for regular solution model. Okay. So in case of ideal, you had only up to this part. You didn't have that delta H mixing term, because in case of ideal solution, this is this was zero. But in case of regular solution, you have this term or extra in your free energy equation. This term is extra. So that is why it is called excess free energy. So basically it is written as delta G of solution regular is equal to delta G solution of ideal plus G of excess. Okay. So G of excess is omega xa xb. So every one of you understood up to this part? Okay, so I think for first few question we have covered enough concept regarding these solutions, regular solution and ideal solution. So now I will move to solve few questions, and then we will cover the free energy versus composition diagram and all. Okay, so let's first few question. Let us solve first few question first. Okay, so this is the first question. This is the question. This is the question number 3 of GATE 2013 metallurgical engineering. So the question is, in a AB, binary system AB, epsilon AA, epsilon BB, and epsilon AB corresponds to AA type of bonds, BB type of bonds, and AB type of bond energies. Okay. So then the miscibility gap will occur if, okay, for to solve this question, I have to cover what is the miscibility gap and this concept. Okay, so I'll be back to this question after some time. So first, let us solve this one. I think because this concept we have covered already. Yes. So this concept we have covered. So this is your integral enthalpy of mixing in joule per mole of liquid copper and zinc solution, and can be approximated by delta H mixing is equal to minus 19250 xcu and xzn. So, in case of regular solution, we found out, right, what is the delta H mix is omega xa and xp. Omega is your interaction parameter. Now you can see this delta H mix that is given, it is almost so it similar kind of form is there. So easily you can find out that omega in this case is minus 19250 joule per mole is total, so it will be joule per, yes, joule per mole. So then the first question is the corresponding partial molar enthalpy of mixing for copper. So again we know that H is a function of temperature, pressure, and it will be also similar like of G. It will also be function of your XA, Na and Nb, right? So we have write down for G also, right? Temperature, pressure, Na and Nb. So there also we found out that G is equal to mu A XA plus mu B XB, or we can also write mu as partial term, partial molar energy GAXA plus GBXB. So this is the partial term. So similarly for H also I can write, or you can write that H of A bar XA plus so this also you can write it. Okay. So now for this equation we have to write in this form, so then only we can consider HA and what is the HB values, right? So in this case A, let's say A is X copper, so X copper and X zinc. A, let's say A is copper and A is copper and B is zinc. Okay, so delta H mix is minus 19250 X of copper, X of zinc. So I think you have understood that question, right? So you have to calculate the partial molar enthalpy. Partial molar enthalpy for copper. That means we have to calculate what is the HA bar. So if you write delta H mixing in this form, and so then only we can compare with what is the value of delta H mix. Like we did earlier in case of G or in case of mu. You remember, right? In case of mu, we have compared it and we find out that mu A is equal to GA plus RTLN XA. So similarly, we have to uh, rewrite or rearrange the equation here, and we have to compare with this equation. Okay. So now let us rewrite this equation or rearrange this equation. So 19250 x of copper, x of zinc, and multiply it by in x of copper plus x of zinc. So this is 1, right? So it doesn't matter if we multiply something by 1, it will be the same thing, right? So let us multiply it by x of copper plus x of zinc. So now if you rewrite the equation, we get 19250 x of copper square into x of Zn minus 19250 x of Zn square into x of copper. Okay, this is your delta H mix. Now compare this equation. Let's say this is equation 1 and this is equation 2. What will be your delta H A bar if you compare equation 1 and equation 2? So in case of delta H A, this coefficient is x of copper, right? This is x of copper. This is x of zinc. So what will be delta H A? Anyone? Anyone? XB square. Yes. XB means zinc. So here you can see that the coefficient is x of copper. Here also the coefficient is x of copper. So delta H A term will be this term. So minus of this. So it will be minus of 19250 x of Zn whole square. So this is your partial molar free energy of copper. Partial molar, sorry, not free energy, partial molar enthalpy of mixing for copper. So what will be the correct answer then? The correct answer will be option D. So every one of you understood this question? Any doubt? Okay. So now let us see the second question. So assuming the regular solution behavior, the solution parameter. So as I derived the equations for the delta H mix for regular solution, so we have seen that delta H mix for regular solution is omega into x into xp, right? So this is for regular solution. So if it is mentioned that ideal solution or subregular solution, then you cannot assume this type of equation. Okay. For ideal anyway, delta H mix is zero, but another type of solution is there, that is subregular solution. So that will I also will explain a little bit. So for this question, it is mentioned that assume the regular solution behavior, the solution parameters. So the solution parameters or interaction parameters, this is omega. So what is the value of omega here? This is minus 19250. So this is your value of omega, right? So in this case, your correct answer is option A. Minus 19250 is value of your omega. So you can directly write that omega or solution parameter is minus 19250. Is it okay? Okay. So let us see for the next question also we have to see how to draw the free energy versus composition diagram. So this question also I will come back after some times, and this question also now we can solve. So this is the question number 26 of GATE 2018. So the question is the molar free energy of a liquid solution of a binary AB alloy as a function of temperature and composition is given by this equation, where so this is the equation where Ga naught Ga naught A is your molar molar free energies for pure A, and G naught B is molar free energies for your pure B in the liquid form. And what is the excess molar free energy for an alloy where X is equal to 0.5? That means your mole fraction is 0.5. So mole fraction of A and B both are 0.5. So and temperature is also given, that is 1000 Kelvin, and gas constant is given, R is 8.314 joule per Kelvin. So option A is 1000 joule per mole, option B is minus 2000 joule per mole, option C is 4763 joule per mole, and option D is minus 5763 joule per mole. So can anyone solve this? So we have already covered this concept today. So now I think easily we can solve this thing. What is the G axis? G axis. What is G axis? Free energy. Just see this equation and what we have derived in today for so what we have derived for regular solution. XA GA naught plus XP GB naught plus RT XA ln XA plus XP ln XP plus omega XA XP. So up to this part it was ideal and this part was excess. So here if you see this equation, it is also similar kind of equation is there. So this is XA, that means 1 minus XP into X GA naught plus XP GB naught plus RT XA ln XA and XP ln XP. So up to this part it is ideal. So up to this part ideal, and this part is your excess. Okay, so that means your G excess is 4 1000 x into 1 minus x. Now x is given, it's 0.5. So 4000 into 0.5 into 1 minus x is also 0.5. So how much it will come? 1000 joule per mole. Yes, Kamesh, you have given the correct answer. Subramaniam, you also have given correct answer. So I think everyone understood this question, right? Okay, so now let us again move to this part and let us see how we can draw the, let us cover the few concept, that is the miscibility gap also. And okay, before going to that concept, let me first describe what is, this is will describe for regular solution, right? But one other kind of solution is also possible, that is a sub-regular solution. So I'm not going to the much depth of this solution model. So only the difference is that in this case, your delta H mix, in case of regular solution, you have calculated delta H mix as omega xa and xp, right? And it is assumed that omega is fixed for like it is independent of your mole fraction or mole fraction of any atoms. Like let's say if you have this phase diagram, so this is 0 to 1. So your omega in this side and omega in that side, it is same value in case of regular solution. So that's why it is a single omega is there, right? But in case of subregular solution, your interaction parameters, it also varies from this end to this end of your phase diagram, or it is like it is also, it is different for your A atom and for your B atom. So that's why in case of subregular solution, your delta H mix will be xa omega A plus xb omega b into xa and xb, right? So this is the only difference between the regular solution model and the subregular solution model. So as you can see here, if you consider omega A is equal to omega b, that is for regular solution, right? You will end up getting this same equation. If you consider omega A is equal to omega b, then if you take the this part is same, so you can take it as common. So it will be xa plus xb into xa xb, and xa plus xb is 1. So you will end up getting the same equation for regular solution. But for subregular solution, your omega A and omega b is different. So that's why you have two solution parameter or two interaction parameter. One is for A atom and one is for B atom. Okay. So this is for the subregular solution. So now let us move to the concept of the miscibility gap and also how to draw the free energy versus composition diagram. So for this thing, so so let us write again the delta G mix. Delta G mix is delta H mix minus T delta S mix. Delta H mix is omega XA XP plus T delta S mix means RT XA then XA plus XP ln XP. This is delta G mix, and G of solution is your G of mixture plus delta G mix. G of mixture means physical mixture. Okay. Now let us draw the free energy versus composition diagram. So let's say this is Ga and this is Gb. So Ga is molar free energy of pure A and Gb is molar free energy of pure B. Okay. So now what will be the G of mixture then? G of mixture is Xa Ga plus Xb Gb is equal to G of mixture, right? And this is let's in the this is Xb. So what will be the how can we plot this G mix physical mixture? it will be simply a straight line, right? XA GA plus XB GB. If we plot G in this graph, it will be a straight line connecting these two points, right? So at this point, your XA is 1. Sorry, yes, XB is 0. That means XA is 1. XA is 1 means, so G mix is equal to GA, right? Similarly, here your XB is equal to 1 and XA is equal to 0. So here your G mix is equal to GB, right? So this line is corresponding to the your G of mixture. G of mixture, that is, but you have one more term, that is delta G mix. So delta G mix is also consists two terms. One is delta H mix, another one is T into delta S mix. So let's say if this line is so from this part you have to sub add this part also and this part also, right? So what is the sign of your omega xxp depends on your interaction parameter. If your interaction parameter is positive, your delta H will be in the positive direction. If it is negative, it will be in the negative direction. Okay, so now let us consider delta omega. Let us consider first omega is negative, let's say. So omega is negative. If the omega is negative, then what will happen? Your delta H mix is also 0. Sorry, in the negative direction. Okay, and also what is the sign of this? Sign of this is always negative, right? Because xa is less than 1, so that means your ln xa will be negative, and similarly ln xb will also be negative. The sign of this term will be always negative, and depending on the value of t, it will maybe more negative or less negative. Okay, so your s is also in the negative direction. So this is your delta H mix, and this is your delta S mix. So if you just like your G of solution is basically summation of this line and these two line. Okay, so your G of solution will be somewhere like this. Okay, so this way we can draw the what is the how the G of any solution is varies with your composition. So this is the free energy versus composition diagram. So everyone is okay with it, or anyone has any doubt? Is it clear to everyone how we can draw the free energy versus composition diagram? So total three part is there. First part is the for mixing. So this is the first part. Then delta H mixing, second term, and then T delta S mix. This is the third term. So sum of these three term is your uh, G of solution. Okay. So this is how we can draw the free energy versus composition diagram. Now let us move to the concept of your miscibility gap. Okay. Yeah. So permissibility gap. So first let us draw the delta G mixing only. Delta G mixing. So delta G mixing. So this is free energy versus composition diagram, and this is, let's say, zero line. This is zero free energy. So there may be two type of scenario may be there. In one case, omega is negative. Another case is omega is positive. So what is delta G mixing? Delta G mixing is delta H mix or omega XA. I'm not writing the whole equation again. I think people have remembered this now. So delta H delta so this equation basically I'm talking about. So delta H mix and minus T delta H mix. So when omega is negative, That means your delta H mix is negative, right? Less than 0. See, your, this is delta. So in this, let's say this is G, H, and S, T, S. Okay. So what will be the your delta H? Then it will be negative. So it will be in this direction, and it is also a symmetrical function with your x. If you see, delta H is omega into x into xp. So it will also be reach maximum or minimum at x is equal to 0.5. It is also symmetrical function. And what will be the delta minus? This is delta H mix. Okay. And what will be the minus T delta S? Minus T delta S will be this one. This is also symmetrical, right? In previous day also we have solved this. We have found out that delta S config, it becomes maximum at x is equal to xb is equal to 0.5. Right? This is also symmetrical. So this is minus T into delta S. So this is always in the negative direction. Now, what will be the delta G mixing then? Summation of these two. So delta G mix will be somewhere here. So this is your delta G mix. Now, let us see what will happen if omega is positive. So if omega is positive, omega positive means your delta H mix is greater than 0, right? Because it is omega XA XP. So delta H mix greater than 0 means it will be like this. But your T delta S will be always negative, right? So T delta S will be like this. So this is delta G mix. Okay. This is not only G of solution. This is delta G mix. Okay. So now your this is your delta H mix when omega is positive, and this is your minus T delta S mix. So what will be your delta G mix? It will be somewhere here. If T is high. So if T is high, that means this term is more negative as compared to your this positive delta H mix. So then your summation of these two will be in the negative direction only. So like if T is high, then delta H mix is less than T delta S mix. But if your T is low, what will happen that time? If your temperature is low, so then this is your delta H term, and then if temperature is low, then this will be your minus T delta S term. Now, what will be the summation of these two? How it will look? So initially it will decrease here, and then it will increase, and again at the end it will go like this. So this is your delta G mix. When T is low means delta H mix greater than T delta S mix. So everyone understood why this energy delta G mixing, this curve will look like this when your T is low. Everyone understood? Okay. So can you also tell me why initially it is decreasing and then it is increasing after some points? Why initially it is decreasing? Can the shape be like this? Let's say your delta H is this one and delta S is this one. So your resultant curve, can will it look like this? in any cases? Is it possible? Anyone? Is it possible? This one. This one is possible or not? Okay. So let me answer. So uh, this type of free energy curve will not you will never get, because uh, you have seen the expression for delta S, right? Delta S config is xa, sorry, minus r xa ln xa plus xb ln xb. So when you are at very end, near this composition or near this end, so that means your xa is tends to 1, or you are at xb tends to 1. What will be your delta S config then? It is almost near about minus infinity, right? Or if you take the derivative of this delta S config by dxa or dxp, anything, and at if you find you will find that just do the derivative and find out. So when you will see that xa is equal to xa tends to 1 or xb tends to 1, okay, there you will get this thing is minus infinity at xa tends to 1 or xb tends to 1. So that means at this two end, your entropy curve is like this curve is has negative minus infinity. The slope is minus infinity. The slope is very high at, at the end of this thing. So but if you see your delta H mix is omega xa xb, right? So but so if you take the derivative, what you will get? So let's see, what is omega xa into 1 minus xa. So if you take the derivative, it will be omega into 1 minus 2xa. So when xa tends to 1, your this value is minus omega, and when xa tends to 0, this value is plus omega, right? So at the end also, your this delta H mixing curve, it has a certain value of your slope is there. So minus omega or plus omega, this is not infinity. So you have a certain value is there in case of your free energy enthalpy curve. But in case of your entropy, so at the very at the pure compositions, that is xa near is equal to 1 or xp near is equal to 0. So your slope of your entropy curve is minus infinity. So every time near your pure compositions, so this is your sorry, this is your delta H, let's say, and this is your delta S. So here it is almost minus infinity. It is slope is minus infinity. So and similarly here also. So that means this value is less than this value. So this value is greater, because near your element, near your pure composition or pure elements, your delta is slope is minus infinity. So that's why always here it will your free energy will decrease initially. Then when this delta H part will dominate minus T delta S part, then it will again increase, and similarly again in this side also, this end also it will decrease. So this is the reason, because of your slope of your delta S curve, because of the nature of your delta S curve, never it will be your free energy curve look like this, because it can never increase, it can never go to in the positive direction here. Always here it will start from the negative direction and then it will go up. So now depending on the your value of omega and your concentration, your free energy curve may look like this. It may look like this also, or it may like, but it will never like this composition. This composition, this will never reach your pure and composition, or x is equal to 1 x equal. There will be always certain gap will be there, or it also may look like this also, like it may not be visible clearly sometimes, but always these two composition, it will never touch your pure composition, or x is equal to 1 x equal to 1. Always little bit negative direction your free energy curve will go, and then it will rise up. Okay, so up to this part everyone understood why this free energy curve looks like this when delta H is positive and at low temperature. Understood? Okay, so now uh, I hope every one of you know, right, that diffusion of any element mostly occurs from the higher chemical potential to the lower chemical potential side. So I am not discussing why it happens, because it is also just some mathematical concept is there, so you can easily find it by yourself also. So, but now let us see how we can get the chemical potential from a free energy versus composition diagram. Okay, so then we'll go to the miscibility gap, that concept. Okay, yes. So what is the G of solution? G of solution, we can write it as mu A xa plus mu B xb, or Ga bar xa plus Gb bar xb. Correct? So now we also have seen that you can draw the free energy versus composition diagram where this is G of solution. We said it is xb, and if this is Ga and this is Gb, this is your line, the mixing line is there, but your free energy versus composition diagram will look like something like this, right? So now let's say if we take this point, this composition, if we take slope here, what will be this value and what will be this value? Anyone? What will be this value? This value, this will become mu A and this will be mu B. It is cutting at xb is equal to 0. That means at pure A side. So this will be mu A and this will be mu B. So how this is coming, I will show you. Like, this is the equations, right, for your g of solution, and this is the slope. Slope means what? Dg of solution by dxb. This is slope, right? And this is slope. So this is a straight line. What will be the equation for this straight line? Y is equal to mx plus c type of equation is there, right? So what is y here? Y is your g of solution, right? And m is dg by dxp, and x means xb, plus c is your intercept, right? So if you write like this, you should get this same equation, right? So now if we calculate del g of del xb, what will it will be? If you derive this equation 1 with respect to xp, what you will get? So if you derive it, dg of del xp, it will be mu a into this xa means it will be 1 minus xp, you can write, right? So if you write 1 minus xp, it will be minus of mu a, right? Minus of mu a plus mu b. So your slope will be simply mu b minus mu a. So this is your slope. So now if you put the value of slope here, so we'll get g of solution. Basically, slope is mu b minus mu a into xb plus mu a. So if you rearrange, you get 1 minus xb into mu a plus xb into mu b. So basically we are getting the same equation. So that means g of solution, this line you can write in terms of this. So this will be your slope and this will be your intercept. And we are just writing this equation in terms of a linear form. In terms of linear form. And so when we are writing in terms of linear form, we are getting that our intercept is mu a and slope is mu b minus mu a. So that's why when this line is intersecting here in the pure a side, that's why what is the value of your intercept? It is mu a. So that's why this point is mu a. So similarly, if you write this in terms of xb, means like uh, if you take plot this, the x-axis is xa. Now we have plot in terms of xb, right? If you plot xa in terms of xa, in this side also we'll get the intercept as mu b, right? So now understood why these intercepts are mu a and this intercept is mu b. Everyone understood? Any doubt? So if we take tangent here from this point, let's say this is x1. So this will be mu a1 and mu b1. Similarly, if we take tangent from some other point, in this case also, it will also touch somewhere here. So here also it will be mu a of for this composition. This is x2. So mu a2 and this will be mu b2, right? So now you can see what is the chemical potential for chemical potential of A for your x2 alloy. Chemical potential of A is less in x2 alloy is less than chemical potential of A in x1 alloy. That means mu A1 is greater than mu A2. What it means? It means your A atom will move from x1 alloy to x2, right? So that means from A rich, this is A rich and this is B rich. So A atom will move from A rich side to B rich side, and B atom will move from B rich side to A rich side. So this is for your when your free energy versus composition diagram, it is in the negative side. But in case of miscibility, or in case of delta, when your delta H was positive, there we saw that delta G mixing curve is look like this, right? And if this is your GA, this is your GB, so this line is the mixture, G of mixture, and this is your delta G of mixing. So now your G of solution will be like this, right? Because G of solution is basically nothing but G of mixture plus delta G mixing, or delta G mix, right? So your free energy versus composition diagram will look like this. So let me enlarge this diagram here. Only G solution will plot. So G solution, let's say GA and GB. So it will be something like this. Okay. Now, if you take any point here and take the tangent, it will cut this somewhere here. So this will be mu A. Let's say this point is 1. So mu A 1. And take other point here. This is mu A. This is, let's say, point 2. If you again take the tangent, it will cut B rich side here and A rich side somewhere here, right? So let's say somewhere on the top it will cut here, let's say. So this will be mu A 2. So in this case, from which side A atom will move to which side? From 1 to 2 or 2 to 1? You can see that mu A 2 is greater than mu A 1. So from which side A atom will move? From point 2 to point 1. But which is A rich? 1 is A rich or 2 is A rich? Which one is A rich? Yes, 1 is A rich. It is B rich. But in case of, if when we will have this kind of free energy versus composition diagram, that means when delta H mix is greater than 0, then if you have any points inside the spinodal or inside this binodal points, your A rich A will move from B rich side to A rich side. Means from B rich side to A rich side, A will move in direction and B will move in this direction. Okay, so this is called uphill diffusion, like up the concentration gradient, like from the A depleted from the B rich side, A is moving from the B rich side to A rich side. So this is B rich, right? This your 2 is B rich, but A is moving from B rich side, not A rich side. But in case of this case, it was your A was moving from this direction to this direction. That is A rich to B rich. But in this case, it is opposite. In this case, it is moving in the opposite direction. So it is called downhill. It is called uphill diffusion. So and because of this, your this creates a miscibility gap in your phase diagram. So if you have this composition, so if you have this composition in your phase diagram, automatically this composition will move this direction and it will split into these two composition, because it will minimize your free energy. So this process will continue when till when you will get a same chemical potential. So if you see, if you draw a tangent covering this point and this point, you will get a common tangent for these 2 points. So what is the meaning of common tangent? Common tangent means this phase and this phase will be at equilibrium because mu a. So let me draw it here, otherwise it is looking very bad. Hmm. So if you draw a common tangent between these 2 points, this is point x and this is point y. So what will be the mu a of point x? Mu a of point x is this point. What will be the mu uh, a of point y? Same point, right? Because the tangent is common to both of these points. So this is also is equal to mu a y. Similarly, in this side, it will be mu b x is equal to mu b y. So that means your chemical potential of A in X phase is equal to chemical potential of A in the Y phase. If your chemical potential is same in both the phases, then it is in the equilibrium, right? It is at equilibrium condition. So then nothing will like so. So these 2 point, what these 2 point called? Anyone of you know what these 2 point called? So these 2 point called binodal point. And what are the spinodal point? Spinodal point will be somewhere here. So at these 2 point, your del square g by del x square is equal to 0. So at these 2 point, this del square g by del x square is 0. So this 2 point is called spinodal point. Right. So now uh, you understood when miscibility occurs and which condition. Which condition miscibility occurs? When you will get this kind of free energy versus compression diagram. Yes, when delta H mix is greater than 0 or omega is greater than 0. So then only you will get miscibility in your phase diagram. And when two phase will be at equilibrium? When the chemical potential will be same, right? Or when there will be common tangent between these two phase. If there is a common tangent between these two phase, then chemical potential of these two phase will be similar. So then your these two phase will be under equilibrium. Is it clear? Is this concept is clear? How we are getting the chemical potential by intercepting at these 2 point, and why atoms is moving from high chemical potential to low chemical potential, and up to this part everything is clear or not? If anyone has any doubt, you can ask me, and then we'll go to solve this few questions covering this concept. So before going to solve those questions, it is important. Okay, so everyone is okay with it, right? So now let us move to the that questions and let us solve these two questions. Okay. So this is the this is the question number 3 of GATE 2013. So in a binary system AB, epsilon AA, epsilon BB, epsilon AB corresponds to the bond energy of AA, BB, and AB type of bond. Uh, and the miscibility gap will occur if option there are 4 options are given. So now as we have already discussed, so miscibility will occur when delta H mix greater than 0 or omega is greater than 0. So omega is greater than 0 means what was the value of omega if you have remember? It was Na into Z into epsilon AB minus of half epsilon AA plus epsilon BB. Right? It was the expression for the omega which we have already derived. So if omega is greater than 0 means with epsilon A B greater than half of. So the correct answer will be option A, right? So it is clear to everyone? Okay. So now let us move to the next question. This we have already solved, right? Now this question. So in that, in case of only one element, like one type of crystal structure, so your free energy curve you can draw like yes. In case of one structure, you can draw free energy curve like this. That is a single free energy curve, right? But when your one end the crystal structure is different than your other end, then what will be then you will have two different free energy curve, not one single free energy curve connecting these two. Okay, so that's why here this two free energy curve has been drawn separately. One is for alpha, so for alpha, so this will also like okay. Let me draw this diagram separately by enlarging here. Okay. You are saying option A. Okay, let us see what will be the correct answer. So let us just draw the diagram here. 1 second. So this is for alpha. So alpha also somewhere it will cut in this side also, and this is let's say for your beta. This is for beta. This is for alpha. Okay. So what was the question? The question is pure metals A and B from two real binary solid solution alpha and beta at temperature T and pressure P. The free energy versus composition plots for both the solution are shown below. The condition for chemical equilibrium. So just now we have discussed what is the condition for the chemical equilibrium? When your chemical potential of A in alpha will be same as the chemical potential of A in beta, or chemical potential of B in alpha will be equal to the chemical potential of B in beta. Is it clear? Because this is condition for chemical equilibrium means we should have a common tangent between these two phases. So when we will have common tangent between these two phases, so this mu, this like here it will be mu of alpha A is equal to mu of B alpha, and sorry, mu of A beta, and this side it will be mu of B alpha is equal to mu of B beta. So for condition for chemical equilibrium is this one, right? So which we have already discussed. Now let us see the options. So first option is mole fraction of A in alpha. What is the mole fraction of A in alpha? This is in terms of mole fraction B. So that means 1 minus this composition is equal to mole fraction of A in beta. This is mole fraction of A in beta. So because this common tangent are touching here, so that's why I am considering these 2 points, right? So is these two composition equal? Mole fraction of A in alpha and mole fraction of A in beta, is it equal? No, right? This is different composition and this is different composition. So it is not equal. So that means this option is not correct, right? So now the second option is mole fraction of B in alpha is equal to mole fraction of A in beta, mole fraction of B in alpha. Mole fraction of B means this one, this composition XB is equal to the mole fraction of A in beta. Mole fraction of A in beta means 1 minus this XB beta, 1 minus XB beta. This also not equal, right? This also different. So this option is not correct. And option C is activity of A in alpha is equal to activity of A in beta and activity of B in alpha. So option C is saying activity of A in alpha is equal to activity of B in activity of A in beta and activity of B in alpha is equal to activity of B in beta. Okay, so how the chemical potential and activity is related? Anyone of you know that? Mu A is equal to Ga plus RTLN activity, right? Just few minutes ago we have derived this thing for ideal solution. For ideal solution we derived, right? Mu A is equal to Ga plus RTLN XA, and for ideal solution activity is equal to XA, right? So this is your activity relationship with your mu A, and we know that at equilibrium mu A in alpha is equal to mu A in beta, right? So mu A in alpha is equal to mu A in beta. Now Ga, it is, what is Ga? Ga is your molar free energy at constant temperature and constant pressure for pure A, right? So this is when T and P fixed, then Ga is also fixed, right? Because this is for pure A. There is no dependency is there with your composition. Only it depends on the for pure A, the G is function of temperature and pressure only. It doesn't depends on your composition. So the molar free energy is, this is also fixed. So that means your mu A alpha is basically proportional to activity. So if your mu A alpha is equal to mu A beta, so that means your activity in alpha will also should be activity of A and beta should be equal, right? Then only your mu A alpha and mu A beta will be equal. Is it clear? Or should I write the expression for alpha and beta separately and then I should describe? Every one of you understood this part? Okay. So that means in this case your correct answer will be option C, right? So I also thought to cover some other concept like in the thermodynamic, the activity for your what is the activity coefficient at gamma, and when you follow the Henryan activity, like for Henryan, when it follows the Raoultian activities, and I thought to plot the your activity of B versus XB that graph also. But for this also we need to cover some more topic like more concept from here. So that we'll cover in the next session then, and then we'll solve this question. So today then, if anyone of you has any doubt, just ask me. I'll explain. And so we are not covering any new topic today then. So today we covered the regular solution model, ideal solution model, and we also have talked about what is the subregular solution model. Okay. And then we saw how to draw the free energy versus composition diagram, how you can get the chemical potential from the free energy versus composition diagram, and what will be the conditions for the equilibrium, right? So if anyone of you has any doubt, you can ask me. Okay. So yes, I will upload this by this like today or maybe tomorrow itself. Okay. If you can go through this recording once again. If you have any doubt, you can ask me in the next session also. That is also fine. So the next session will be from 6 to 7. So only this session was from 5 to 7. So next session onwards, next Sunday onwards, I will take class from 6 on. Okay. Okay then. If no one has any doubt, then we'll meet again on next Sunday.